Okay, today I am going to talk with you about the results of the pressure versus number of particles lab, otherwise known as the P versus N lab. And first, I'd like to take a look at the graph. So your graph will look something like this, but we want to add some more details to it. You may have already added your trend line, but just in case you haven't, we're going to do that. So you can either double click or click Edit Chart. And under Customize, the Customize tool, we'll go under Series and then scroll down. And when you scroll down, click the box that says Trend Line. And unlike the last lab with pressure versus volume, this trend line is linear, so we can leave it on the default linear trend line. And then when the label, mine already is on label for use equation right here. If yours is not, change it to use equation. Now you may notice that the x-axis, for mine at least, Google has defaulted to have it not start at 0. And I would like the x-axis to start at 0. So I'm going to scroll down a bit further to where it says horizontal axis, and it kind of defaulted to go down. So I'm under the horizontal axis menu, and where it says minimum value, I'm going to type in a 0. And when I do that, then it will make the axis go all the way to 0. Now, the reason this is important is because when we did the pressure versus volume lab, the curved line we had never touched 0. It had 2 asymptotes. So the pressure was never able to reach 0 because no matter how big we made our syringe, eventually one of those particles would collide with the side and there would be pressure. And no matter how small we squished the syringe, because there was particles in it, then those particles had a volume, and the volume could never be 0. So with pressure and volume, neither side of the curve reached 0. But in this case, we're doing pressure and number of particles. And logically, if you have 0 particles in your container, then those particles, since they don't exist, can't collide with the container. And so there would be 0 pressure. So this graph should go through 0, 0. And if you look at our equation, my equation is 10.4x plus 0.66. The 0.66 is the y-intercept, and it should be very close to 0, because if we had perfect data, it would be 0, because 0 particles will have 0 pressure. So if yours is very far from 0, you might want to double check your data. If there's one data point that's really far off your line, you can sort of delete it as a mistake, and it might improve your data. Now, as we saw from before, when we did our density graphs, we will think a little bit about this equation, but we're actually going to process the data in a slightly different way that's more similar to what we did with the previous lab. So I'm going to go back to my data screen. And on the data screen, it's scrolled down here, there we go, now it's scrolled back up. You'll notice that I have my particles column, my pressure column, and then I've made 2 new columns. I made one for pressure times number of particles, P times N. Remember, in spreadsheets, the star is the times sign. And then I have one for pressure divided by number of particles. So I'd like you to do the same thing. And then we are going to make this spreadsheet do math for us. So to do that, the first thing we need to do is type the equal sign, because that lets it know we're doing math now. And then you will click on your column that has pressure. So for me, that is column B. So I'll click just once on the first cell in the pressure column, which is B2 for me. And then I will click times. Remember, times is the star. So I'll click times, and then I want to click the first one in the particles column. So now we have equals B2 times A2. And now we will press enter. And when we press enter, that will make it into it will show the answer, but it also records it as an equation. So if you look down here, it shows the number that is B2 times A2. But then if you look up at the top, you can see that it's still recorded as an equation. So it's still thinking of it as an equation. And we want to do is copy this equation down to all of the rest of our cells. So to do that, you hover over the circle here, and you'll notice my cursor changes to a cross. Then you click and hold and drag it down, and then unclick when you get to the bottom, and that will do the same math for every row. Now, I previously was using this for other examples in other classes, and I changed the decimal places. So up here at the top, you'll notice there's an increase and decrease decimal places. So I can increase them, I can decrease them. So I decrease the decimal places to have it rounded to the ones place, because in this case, that's all all the sig figs we need. All right, now we're going to do the same thing with pressure divided by particles. You do the equal sign, then you click on the pressure column, and then divided by is the /, and then we click on the particles column. We press enter, and notice Google helpfully offered to autofill. If it does that for you, just agree, because then you don't have to do it. Remember, if it didn't do it for you, you'd click on it and you'd click and drag on the circle all the way down. So now, if you remember pressure and volume, pressure times volume was equal to a constant. Now in this case, pressure times particles, if we look here, it just seems to be a number that's getting bigger and bigger. It's not the same number every time. But if we look at pressure divided by number of particles, you may notice that these are all very, very close to the same number. So we could call that a constant. Now, thinking about our graph, pressure divided by particles, pressure is the y-axis, particles is the x-axis. That's rise over run. What we're looking at is the slope. And you'll notice that the slope on my graph is in fact 10.4. When we did our density lab, we were interested in the value of the slope because for every metal, density is always the same number. But one thing you might have noticed when you're doing this on your data, because hopefully you were following along and doing this on your data as well, is that your constant is not the same as mine. In fact, yours is probably near 5, because when you guys use the volume of 20 milliliters, you end up with a constant that's close to 5. When I made the sample data, I used 10 milliliters as my volume, and so my constant is not the same as your constant. And that's not very useful to us, because if the constant changes every time, that could be really confusing. But we can still use this to do math by doing the same thing that we saw previously. So we looked at this last class, and we saw that we can think about two of the points and use them to make an equation. So let's go for blue here. So I'm going to think about these 2 points right here, because they both equal 10.4, which was the slope of my line. So point 1, we're going to call the pressure at that point P1. And we saw that P1 divided by N1, the pressure divided by the particles at that point, is equal to a constant. And K is a letter that we often use for constants in science. Now, if we think about the second point there, we'll call that P2. And the pressure at that point divided by the particles at that point is also equal to a constant. So because the pressure divided by the particles at one point is equal to the same constant as the pressure divided by the particles at the second point, that means using our rules of math, if they're equal to the same number, which in this case is 10.4, and in your case might be something like 5.1, we can say those two things are in fact equal to each other. So P1 divided by N1 is equal to P2 divided by N2. And now it doesn't matter what our constant is. If we know the pressure and the particles at one point, we can find the pressure and the particles at a second point. So this relationship is our second equation. And the previous one, if you recall, was Boyle's law. This one doesn't have a specific name, but it is a variation of a similar equation called Avogadro's law. So this is a variation of Avogadro's law. So Avogadro's actual law is the relationship between particles and volume. So we've just adjusted that slightly to make it particles and pressure. And if Avogadro's name sounds familiar, he's a very famous scientist. We'll talk about him more later in the year. He's the one who will help us learn how to count particles more precisely. But for now, we'll just think of him in terms of his law. So now, as you can see on your worksheet number 3, which you will be filling out with this new information, if you are given the pressure and the particles at one point, and then you're given either one of them at a second point, either pressure or particles, you can solve for your unknown variable. So you can do the practice problems and see how it goes.